Hello, I'm Nicholas, and welcome to the Wolfram Tech Conference. I'm a math content developer with the Wolfram Alpha Math Group, and I'm also a PhD candidate finishing up at Indiana University, wherein my research consists of molecular dynamics simulations for the most part. We'll be focusing today, amongst the other 12 talks I'm sure you're attending, on the Wolfram language's ability to facilitate molecular dynamics workflows. So in particular, the exemplary case of nanoparticle self-assembly simulations. I won't dwell on the abstract for too long as it's just an outline of the talk. I'll pause here momentarily so that if you're in the web-based version in the future, you can read this if you so choose, just by pausing the video. I'll take this chance to thank my mentor, Vikram Jadhav, and our experimental collaborators, Trevor Douglas and Masaki Uchida, all of whom are at Indiana University, for contributing to the some of the content that you'll see today. So we'll start with just an overview of molecular dynamics. So traditional physics, the stuff you encounter in your classes, employs pen and paper theory in order to do symbolic calculations, exact calculations, mathematically on solving the dynamics of a given system. For example, you could analytically predict the motion of, say, a massive negatively charged particle on the left and a smaller positively charged particle on the right. And you could predict things like the equilibrium position of the two based on the forces of attraction and repulsion. For example, if there is coulombic attraction between the charged entities, but steric repulsion due to their finite size, there would be an equilibrium position such that, for example, the smaller, lighter, positively charged green particle would condense on the surface and come to rest on the surface of the larger particle. These kind of calculations have the same setup as simulations would, where you have initial conditions, positions, particle properties, etc. And you have particle interactions, energies, forces that are parameterized by the properties of the particles. And for simulation setup and more complicated pen and paper problems, you have to take into consideration the thermodynamic ensemble and other elements of the thermodynamics of the problem. This is easy enough to do on pen and paper for, say, a two-particle system. There's a complicated problem in physics called the n-body problem. And those of you that keep pace with the Wolfram language's developments generally know about n-body simulate, a new function that they've introduced to numerically integrate such systems. Molecular dynamics is a similar implementation of numerical integration of systems that are too complicated to do analytically on pen and paper. So they're analytically insoluble, but you still want to solve and say something about them. The exemplary case we'll study today briefly is nanoparticle self-assembly. So if you want to simulate this, why is it important? What is it, etc. So it's the nanoscale equivalent of colloidal agglomeration, if you've heard of that. Essentially, at different length scales, particles stick together based on the solution conditions relative to their properties. So like charged particles will have steric attraction, but electrostatic repulsion. And this leads to, in low salt conditions where the electrostatic repulsion is strong, they don't assemble. And as they go into lower salt conditions where the electrostatics, or higher salt conditions, excuse me, where the electrostatics is weaker, the attraction due to sterics overwhelms that and the particles stick together. This is the phenomena, or one of the phenomena, that leads to river delta formation. So freshwater to saltwater transitions changes the electrostatic screening between like-charged particles. This leads to sedimentation and river delta, or the mouth of rivers, their formation. We also exploit this in technological applications, such as paper making, cheese making, water treatment, where you want to rid yourself of any impurities. And my collaborators use this specifically for the purpose of catalysis, or the speeding up of reactions, wherein if the larger particles, which happen to be hollowed out viruses, the shell of viruses, you can put your own cargo in there that's enzymes, substrates, reactants, that if the local concentration is driven up by the self-assembly process, the local proximity of particles leads to higher concentrations locally, reactions will speed up by, I believe they said 10 to 20 fold. So how would you go about modeling this process of particles going from a dilute suspension to a concentrated array assembly? There are three phases to any process of molecular dynamics simulations, and that's preprocessing and setup, conception of the problem, once you've conceived of the problem accurately, communicating that to your simulation software, which is the central cog here, and then post-processing and analysis. And we'll go through each of these phases individually and the extent to which, in its current state, the Wolfram language can contribute to the process. So pre-processing and setup consists of a lot of the stuff we've already talked about: specification of initial conditions, particle positions, particle properties such as charge, any steric repulsion, etc. The selection of forces that represent that steric repulsion, the charge-charge interactions, etc. Specification of any thermodynamics, what temperature you're at, for example, and specification of this stuff in a format that the computer can understand. And so this involves the exporting of data files, the exporting of input scripts that specify the physics of what will happen during runtime, etc. And we'll go through each of these sequentially. So initial conditions is straightforward. We've discussed this. You have a box that you intend to run your simulation in, which is often referred to as a unit cell. In this unit cell, you have, say, 100,000 particles that you intend to explicitly simulate. You specify the concentration by saying the box is of this size, the number of particles in the simulation is n, and you simulate a certain concentration, which is important to the experimental collaborators you have because there are specific concentrations or packing fractions at which the phenomenology occurs and at which they're able to do the experiments. And once you've done this by, say, using random real to enumerate the particle positions in your box, using table and if statements to do the enumeration sequentially such that particles aren't overlapping too much so that there aren't numerical issues as you start your simulation. For example, if the particles are overlapping too much, the force will be very high and the particle will shoot out of the box in the first time step. To avoid small problems like this, you can enumerate particle positions such that they're not overlapping and then export that in a file that will communicate to your molecular dynamics software. The analysis of the parapotentials, so you've populated your box, you've told it what's going to be in the simulation, but you haven't yet told it how is it going to interact. You might not have conceptualized even how are these things going to interact. During that conceptualization, so the figuring out of what will happen once you press go in the simulation, you have to know what are my parapotentials in the simulation. This is where Mathematica traditionally shines as a, from day one. And that's in using things like everybody's beloved manipulate with a plot in order to analyze the parapotential, the energy of interaction between different particle types. For example, here I've shown the parapotential between particles as a function of their separation distance, varying the parameter sigma, which corresponds to the rigidity of the particle. So billiard balls bounce off of each other pretty abruptly when they collide. How abrupt is that repulsion upon collision as a function of R? Of course, once you have a potential function, you can use the derivative and gradient to calculate the force involved so that you can plot and analyze the force. And Mathematica shines, of course, by doing symbolic calculations to the extent you can for simulation setup and helping you conceptualize your problem in that fashion. Once you've conceptualized the problem, you've got your data file to communicate the initial conditions to the simulation. You've got your parapotentials conceptualized. You need to formalize those in what's called an input script for the third-party software, whether it's a self-written C++ code or a third-party software you simply downloaded to do molecular dynamics, such as LAMMPS or GROMACS. You need to communicate what potential functions you want to use in an input script that the computer can understand, that that software can understand. And so Mathematica can do the calculations for what are typically, say, thousands or tens of thousands of simulations that you need to do for a given project, where you have a multi-dimensional parameter space. So you have 5 parameters in your potential function. You need to assess the aggregate effect of varying each of these, such that you don't have the luxury of doing one simulation. You have the privilege of doing 10,000. And it's a privilege because Mathematica can automate that process for you, such that it will write input scripts depending on the parameters that you specify rather than you having to slave through those calculations by hand. So once you've written the input script or the 10,000 input scripts for your batch simulation submission, you will have a submission script to accompany that specifies, say, the number of processors, the wall time, etc. For example, you need to tell the supercomputer, I want to spend about 2 weeks with 128 processors crunching on this, and it should generate about 8 gigabytes of data. And well, the Wolfram language can help set you up with a folder hierarchy that has these input scripts, submission scripts, initial condition data files, in them so that you can submit your 5,000 jobs and then go work another job or on another project entirely while those simulations run for those 2 weeks. So common functionality in the Wolfram language that will help you in this process are the functions like export, create directory, copy file, etc., because these are essentially formatted text files. So while a lot of the heavy lifting, the 2 weeks, 128 processors stuff is done on the supercomputer, it sounds like that would be where most of your time would be spent. But typically you can download third-party softwares, or you've already written a software yourself that in a lower level language, for example, that does molecular dynamics, such that not a lot of your development time, particularly if you just download a third-party software, is spent in this phase. So while the computational heavy lifting is done here, for example, I use a third-party software called LAMMPS, and I submit my batch jobs. They're going to run for 2 weeks, and then I go work for Wolfram during those 2 weeks while this process is, while the simulations are running. So often very little development time is spent on this phase relative to the elements that the Wolfram language as it is now can help with more, which is pre-processing and post-processing. So moving on to post-processing, this is where you stand to really expedite your workflow. So the unclear haze associated with the analytical insolubility of the problem, many body problems, for example, this carries through to the analysis. So you don't know exactly what variables you're solving for. You don't know exactly what's going to happen because you can't solve for the variables even if you knew what they are. And so you need to compensate by doing a lot of exploratory data analysis. And typically in my experience in a molecular dynamics project, exploratory data analysis gets published at about a 10% rate, such that you do a lot of exploratory data analysis that, oh, this doesn't indicate an underlying kinetic or thermodynamic mechanism. And so we're going to throw that analysis out and we're going to proceed with a different type of analysis. You have to be fast in doing this. Otherwise you will drown in the amount of exploratory data analysis you need to do. And the Wolfram language is uniquely poised to expedite that workflow. So the different types of post-processing you'll do are visualization, simple snapshots as you see here, quantitative analysis to get at the kinetic and thermodynamic mechanisms quantitatively, like you would do in a traditional physics problem, and quantitative analysis such that you understand exactly what is going on physically in the simulation, for example, structural inferences, etc., the spatial statistics, for example. So visualization is obviously useful. You know, the Wolfram language is great at that. It is incredibly useful to see what's happening before you go to analyze it. You know, a lot of people are visual learners. You know, those kind of cues are important in not only understanding what happened in the simulation, but in corroborating the observations that can be made experimentally. So here are visualizations associated with a project that I worked on for the Nanoparticle SelfAssembly, where you can see the plot label here varies from left to right, increasing salt concentrations. So as you titrate salt, you see a pretty drastic variation in the propensity for self-assembly, where in some ionic strength conditions, salt conditions, you see extensive self-assembly, and in some you see no self-assembly at all. There's the electrostatic screening effects we were discussing briefly. And similarly, you have the same left to right transition in the bottom right figure where without a microscope, without anything, you can see the optical density shift from an opaque milky white when there's an assembly condition, like salt concentration such that assembly occurs, to a translucent color where there is no light scattering because there is no assembly. And similarly with microscopy techniques, you can visualize this assembly process where the array has formed in the bottom half of the panel in the bottom left figure. And so corroborating visualizations between simulations and between experiments is the initial thing, and sometimes for biochemists, for example, the only thing that people want to see, right? This, you don't have the luxury of looking at, say, even just 4 simulations like I showed you there. Those were cherry picked from often dozens, hundreds, thousands of simulations. And so the ability of the Wolfram language to, instead of opening up a visualization software, scrolling to the end of your time series, the last snapshot of the video, and taking a screenshot, and spending your entire life doing that with every condition for those thousands of simulations, a simple command where if you've written a function that will visualize your simulation mapped onto the simulation directories that you found using, for example, the function find file, which will find output directories as well. If you simply map this visualization function onto your simulation directories and use multi-column, it will produce a nice panel where you've titrated salt. If you can see the very small text in the plot label, this is a 10 millimolar salt condition, 25 millimolar salt condition, 50, and so it goes left to right, top to bottom. And so the ability to scroll through these expeditiously rather than, say, taking snapshots and putting them in a PowerPoint is incredibly valuable and will triple the amount of projects you can work on per unit time if you do it properly. And so moving on to quantitative analysis, how do you enhance this picture with quantitative data? We'll brush through this quickly such that you have the snapshots that you have on the bottom left. You have the same titration and salt on the x-axis for both quantitative plots you see here. The top left is an experimental assessment of the optical density. So how opaque is that solution, where it peaks for assembly conditions and goes down for non-assembly conditions. In some forms of light scattering, the radius of gyration is what determines that. We've used a WFR that I've created to give an estimate of the radius of gyration of these particles, the assemblies rather. And you can see that while it's not a one-to-one correspondence, we wouldn't expect it to be in this case, there are the same behaviors where you have a domain of assembly and a domains of non-assembly. This ability to take a time average with, say, a Wolfram Function Repository function expedites your workflow orders of magnitude over what you would come to think C++ could do. Right? If you did all of this coding in C++, we'll get to a more quantitative example later, but it will slow you down considerably. One other example of neat quantitative analysis that you can do with these kind of systems is on the left, you have a cannonball stacking. It's called an FCC or HCP lattice. I believe HCP here, but don't quote me on that. The two are very similar. They're close packed, rigidly spherical lattices. And a cannonball stacking is what you would see if you walked into a war memorial, you walked onto a pirate ship, etc. From the visualization in the center, you can kind of think perhaps that's a similar stacking. And if you look at the radial distribution function, also known as a pair correlation function, you can see that indeed the grid lines here, we won't get into what this is for the purpose of time, but the grid lines here correspond to where you would expect peaks to be were the nanoscopic lattice, the same as what we see for cannonball stackings on human length scales. And indeed, you see peaks at those positions such that it is indeed a cannonball stacking, despite the huge change in physical mechanism from gravitational forces to electrostatic forces. The underlying mathematics of stacked rigid spheres and the close packing nature of those lattices is the same. And so this can be done by simply using this resource function for the time being. I believe spatial statistics functionality is being added such that you might find this as a kernel function that other developers have worked on, which would be great. Such that similarly to visualization, you have a function that you've written that you then map onto your simulation directories. There's a little bit extra because you have to take a time average of your data, which you import using a file stream or something. But that's the bare bones structure of how you would conduct this kind of analysis, such that you can show interesting phenomenology beyond just looking at simulation visualizations. So the Wolfram language can enhance your workflow drastically by providing preprocessing and setup functionality to allow you to expeditiously submit thousands of simulations after you conceptualize the problem. And it can help you do post-processing and analysis expeditiously such that you don't have to do it in a lower level language like C++. There are community development aspects to this where if you'd like to not only enhance your own workflow, you'd like to enhance other people's workflow, you can write Wolfram Function Repository editions as I've done here, where if you click one of these hyperlinks when you download the notebook later, for example, if you so choose, you can go and find the source code for this such that other people can use it as I had highlighted in the previous slide without writing any code on their own. And that's truly the power of higher level languages like the Wolfram language, particularly now that it's more community driven with the function repository. So the function repository offers you the ability to contribute to Wolfram language development and if you're a self-promoting type, to promote your work as a citation in the metadata of the function repository edition. So I've cited my own paper here where I use this functionality upon contributing it to the the repository. So if we go to a summary, I want to highlight more clearly in post-processing and analysis, the third phase here highlighted in the gear diagram, the extent to which you can speed up your workflow by working in a high-level language. So I've written, and other people more seasoned than me, I've had about 3 or 4 years in C++. Other people that I've talked to who have had, probably about 10 years of C++ experience, we wrote a function to do the radial distribution function, about 400 lines. It didn't have error handling. It wasn't terribly robust, but it did the job. And that took about 400 lines. It was fast because it was C++. The comparable functionality in Wolfram Language takes about 4 lines. So instead of writing 400 lines for several days, you write 4 lines in an hour or 2. It's incredibly efficient in troubleshooting to look at 4 lines if there's a mathematical problem and find it immediately. In fact, I had to use my Wolfram Language functionality and the clarity I had there to troubleshoot why the C++ and the Wolfram Language instantiation didn't match, because the C++ had so much code fog that I couldn't see the mathematical mistake existed at first. A robust contribution such that has error handling, it won't crash your kernel, it doesn't accept bad inputs that would crash your kernel, etc., is about 70 lines in the Wolfram Language. So still more than a factor of 2 lower than the C++ requirement. Additionally, this auto compiles to C for speed, such that you can, in 70 lines, produce something that has the speed benefits of a low-level language without having to write the low-level language code yourself. This is reminiscent of this 4 lines to 70 lines of being able to do 2 to 100 times more lines of code in a lower-level language, is reminiscent of I think a blog post I saw recently, or a marketing thing for Wolfram, saying that you can get something interesting in less than 5 lines, and that's absolutely true. And so in an academic environment where 7% of PhDs are seeking academic positions because of the job market, the enhancement of your workflow allows you to publish rather than perish, publish, not perish, by working on multiple projects at the same time, rather than getting overwhelmed with trying to work in a lower level language entirely. And the auto compilation bridges the efficiency gap between the two, the low level languages and the Wolfram language. The future of the Wolfram language, doing molecular dynamics system simulations directly such that we can eliminate that central cog of a third-party software, lies in this ability to self-compile. So self-compilation is already used in a variety of applications to greatly speed up Wolfram language code. Hopefully someday it will be used to run simulations themselves in the Wolfram language such that you don't even have the need to communicate with a third-party software at all. And HPC or supercomputer support for Wolfram language already exists. So with that, I'm happy to take questions. I think I've probably gone over a little bit on the time. Feel free to email me at nbrunk@wolfram.com or set up a time to meet during the tech conference in off hours. Thank you.